Hello students and welcome to lecture 5 of mechanics of materials. In this lecture we are going to talk about what is fatigue failure, how it occurs, and what is this SN curve and how we can use it to keep our materials safe from fatigue failure. So previously we did discuss that when you have a stress and it is increasing with time, like shown here by the dotted line, you have certain stages or the stress strain curve develop. This is what we do in the universal testing machine, UTM, where you apply a stress and you keep on increasing it, and then you get to a point which is proportional limit, then yield strength, and then at a certain point you get to the ultimate strength where your body fails. Okay, your material fails, it get a fracture there. Okay, so this is what we have studied so far in the previous lectures. But there are cases where your material may fail much below the yield point, even somewhere here maybe. Okay, so this happens when you do not have this linearly increasing load, or you do not have an increasing or decreasing load, but you have a cyclic loading. Cyclic loading is actually fluctuates between two points, which is one maximum, one minimum, and then it keeps on repeating. So this loading keeps on repeating its cycle, and in this case when we have cyclic loading, it is much possible that your fracture will occur below the yield point as well. So you do not apply the stress required for the material failure, which is the ultimate strength. uh, it usually just fails at any stress even below the yield point when you have cyclic loading, and 90% of our mechanical failure occurs because of these cyclic loadings. So it is very important to actually understand this cyclic loading and how we can prevent our material from failing it. Okay, so fatigue failure is actually a progressive and localized structural damage occurring when material is subjected to repeated, so very important, repeating and fluctuating stresses, often below the yield strength. So the fracture occurs even below the yield strength. You do not have to apply the ultimate stress to actually get the material failed. For example, if you look at this shaft, so if this is rotating, let's say in this direction, and you have, let's say, the force applied F from the top. Okay, so we are applying this force. What happens is that let's say I draw the cross section of the shaft. So at one point the force is applied here, okay, at this specific point of the shaft. Then when the body rotates, okay, then let's say that this point comes to the front of the force, and then even rotates further, then this is now in front of the force, then this point. So what happens is this point on which the force is applied keeps on changing, and after some certain time our point 1 that was here, okay, it will again come in front of the force. So what happens is that you have applied a force on point 1, and then after a certain time you apply the force again on it, and then after a certain time the force is applied again on it. Similarly, when this point 1 comes at this point, okay, so it is now below this point, so that would means that now your force applied is totally opposite. Okay, so on point 1 initially the force, let's say it was applied something like this, but when it is at position, let's say A, okay, then the force applied is totally opposite. Okay, so it is kind of a cyclic loading applied on this shaft. So when this is the case, we have the failure that occurs is generally known as the fatigue failure, because the force applied is actually repeated, it is cyclic, and it is progressive. There are certain kind of loadings, so let's go on and discuss one by one. First one is the fully reversed cycle, which means that your whatever is the positive load, that the same is your negative load. So if positive is 3, you get the negative 3. So it is fully reverse cycle. In other words, let's define some terminologies so that we can actually understand and quantify our signal well. The first one would be our minimum and maximum stress. So maximum stress, we have whatever is the maximum value of the stress, and minimum is somewhere here, so we have the minimum value. Then we go on to the stress range, which is actually the difference between the maximum and the minimum. Okay, keep in mind that, for example, if the minimum is a negative value, for example here it is -3 and the maximum is +3, so your stress range will be actually equal to the maximum minus the minimum. Okay, so you will actually get the range, which is sigma r equal to +6. So this negative negative become positive. Okay, so that is how you calculate it. So you have to keep in mind the negative values and the positive values. Okay, so that will give you the stress range. Additionally, we need to know the amplitude of the signal. So that is actually whatever your range is. So whatever the stress range is, it would be half of the stress range. Okay, so you divide it by 2. So sigma mx minus sigma minimum. So you do the sigma maximum minus sigma minimum. This gives you the stress range, which is this line, and then you divide it by 2. So this gives you the amplitude. Amplitude is generally the maximum displacement from the mean position, okay, of the force. So if this is the mean position, so it would be half of the total range of the stress. Okay. Finally, we have a very important terminology that we'll be using moving forward, will be the mean stress, which is actually given by sigma max plus sigma min divided by 2. Okay, so maximum stress plus minimum stress divided by 2. It is actually showing that what is the mean or average of this signal. Okay, so you take the maximum value, you take the minimum value, you add them up and then divide it by 2. In this case, the maximum is, let's say, in this case it is +3 and then you have a -3. So your mean or sigma m will be equal to the maximum plus minimum divided by 2, and you will get sigma m equal to 0. So in this case the mean is equal to 0, so the average actually stays on this horizontal line here, and your mean stress is equal to 0. Okay, what this is actually, that is why it is termed as the fully reversed cycle, because the mean stress is in this case equal to 0, and whatever is positive you get the same value on the negative side. So whatever here is positive, you get the same on the negative side. So that is why this is called the fully reversed. What if the sigma mean is not equal to 0? Like, for example, it is possible that a force applied on one direction is not equal to the force applied on the other direction of the shaft. So that would be our fluctuating cycle. So in this case, you can see that the signal is shifted forward. So you have more on positive. So let's say this is positive and you get here something negative. So positive is even more than 4 and negative is less than -2. So that would be giving you sigma mean, which is this value, something, let's say this is 4.2 and this is 1 point, let's say 8. So you get what, if you try to calculate sigma m or mean stress, that would be maximum plus minimum, which is -1.8, as this is on the negative side, and then divide it by 2. So you get sigma mean equal to somewhere greater than 0. Okay, so when that is the case, then you have a fluctuating cycle instead of a fully reversed cycle, and this will have a whole lot of different fatigue analysis. So when you are talking about fully reversed cycle, the fatigue analysis would be rather different, and that is why we need to understand that what kind of loading is applied on the component. Then there is a case where you have a fluctuating cycle. In this case, sigma mean will either be greater than 0 or less than 0, depending on which side of the axis the cycle is on. Like, for example, in this case it is on the positive side, so you have this positive axis, and then that is why your sigma mean is greater than 0. But it is possible that signal is on the negative side, so it will be less than 0. But in a pulsating side, it will be always not equal to 0. The sigma mean will not be equal to 0. Okay. Also, you can actually get the amplitude. So in this case, amplitude would be something like this. You see the it would be from the mean position, whatever the distance is from the 0 axis. Okay, and then when the failure occurs due to these applied loadings, it occurs in 3 stages. Initially, crack initiate at the surface. So you can see that if you drill a hole in this and then apply some loading, which is cyclic, it will start a crack. So that is kind of initiation. Then you get the crack propagation. So the crack increases into the surface, so that propagates due to the cyclic loading. And finally you get the fatigue failure. So as it propagates, you get a failure of the component. Okay, so it has these 3 stages. In the first one, the crack initiates. It initiates due to the surface roughness or surface not being the good quality, or maybe the load or too much, so it initiates the crack. Then it propagates slowly, and finally it cracks. So whenever our failure occurs, it does not occurs like instantly. So it has a kind of a long time between the initiating and the failure, and that is when the crack is actually propagating. So sometimes we might not notice and we think that our equipment is working fine, but actually that crack is propagating slowly due to the cyclic loading applied on it, and finally eventually it will break, so everything fails. Then we do these testings for each material to actually know what are the number of cycles of loadings that it can sustain for a given stress. So we draw this graph. This is a very important plot where on the horizontal axis you have the number of cycles to failure, on vertical axis we have the applied stress. So we apply a stress and we try to check at what number of cycles the equipment or the part actually fails. Okay, so when you do the testing for, let's say, one specific material, you will actually get something like this. So you do one test, you get the failure at, let's say, this number of cycle when the stress is applied here. Okay, and then you do another test, you get, when the stress is reduced, you get more number of cycles. It actually runs for more cycles and then fail. So as you keep on reducing the stress, okay, you will actually be able, the equipment will be able to sustain for more number of cycles. Okay, so these testing need to be done for the material to actually understand what are the fatigue limits for that specific material. And then what we do is, when we have all these points for a material, there is a fit curve that actually fits these data points. Okay, and this is actually called the SN curve. A very important curve, because whatever material you are using for a cyclic loading, you need to know what is the SN curve for that in order to be able to stay within the safe limit. Now, as you can see, it will actually, this curve will actually tell you, for example, if you are applying this much stress, so it actually can tell you that it will fail at this specific number of cycles. So it will fail after 10 raised to power 5 number of cycles and less than 10 raised to power 6 number of cycles. So it can actually tell you for sure that your component is going to fail at this specific number of cycles. Okay, and for example, if you are having a component that on which you apply 100 megapascal of stress, so you apply this specific amount of stress, and you have this SN curve for that material, and it actually tells you that it will fail after 500,000 cycles. Okay, let's say you are applying it on a you are installing it somewhere where you need 1 cycle per minute of that cyclic loading. Okay, so you can actually calculate that how long will it take for that material to actually sustain there. Okay, and after how long it will fail. Okay, so you can actually calculate that because it has 500,000 cycles of lifetime, and you are having 1 cycle per minute. That means you will have 500 thousands of minutes, because each cycle, in 1 cycle in 1 minute, that would mean that after 500,000 minutes your component will fail. So that would give you, actually you can convert it into um, hours dividing by 60, and then you convert it into um, days, whatever you want to do. So you want to count days or years, so roughly it will give you 1 year of lifetime. Okay, so for this specific material on whose the curve you have, so this, let's say this is ferrous material. Okay, so this is the curve for that. If you apply 100 megapascal of cyclic loading, it will give you 500,000 cycles to fail. And if you are applying that load, this 100 megapascal load, 1 cycle per minute, then you will have the component will fail after 1 year. Obviously you are not going to buy something that you for sure know will actually fail after 1 year, roughly 1 year. Okay, so you are not going to buy anything like that. And that is why what we see here is, as you go reduce the stress, okay, you get more number of cycles. You reduce the stress, you get more number of cycles, and at certain point this line becomes horizontal. So when you go below that line, you actually get do not get the failure. Okay, so that is the region that we call the infinite fatigue life region. Okay, that is below this specific horizontal line, and this limit below which this occurs, we call this limit as the endurance limit. So if you have a cyclic loading, you would want to stay below the endurance limit in order to have an infinite fatigue life. Okay, so if you are designing something, you would design it to last as long as possible. You will not design something that you will know that it is going to fail after this number of cycle. Okay, so this is what we call the endurance limit. And then there are certain classifications that we did. So in first case, we have the low cycle fatigue. So that means your stresses are actually too high. Like for example, if you look at this curve, for this curve you will need to have quite high stresses, so you will actually get the failure with very much less number of cycles. Okay, and that is why if you have this scenario, you will have a high stresses, small number of cycles. So that means if your stresses are too high, okay, you will have a small number of cycles. The body will fail with the small number of cycles. Okay, or it will fail quite early, and this happens in the plastic deformation region. So if you look at this stress strain curve on the right, you would see if you are applying something like, for example, this much stress, so your body is going to fail here, and this is actually in our plastic deformation region. Okay, this is in the plastic deformation region, which is between this and this curve. Okay, similarly, if you have a high cycle fatigue where your stresses are low, so you are actually dealing, let's say, with low stresses, it will fail. If you are dealing with the low stresses, let's say this one, so it will fail with the high number of cycles. Okay, and that is happening in actually elastic deformation region, so which is actually this region right here, elastic deformation, and it might be somewhere here. Okay, it might be somewhere with at this stress. Okay, but usually it is below the yield point. So most of the time this SN curve is very much feasible for high cycle fatigue. It's not very much feasible for the low cycles fatigue, as you see the difference between the stresses are quite tight. Okay, and you get the very low number of cycle to fail. So that is why we want to actually have the curve used for the high cycle fatigues where elastic deformation is involved. And when we define the fatigue stress, we said that it can fail below the yield point uh, when the cyclic loading is applied. Now, this endurance limit is good enough, and we can actually get the infinite fatigue life in this case. But the issue is this is specifically designed for a cyclic, fully reversed cycle where mean stress is equal to zero. Okay, so if your mean stress is not equal to zero, then it is a big problem. Then what would you do? Okay, you cannot have this curve for all the mean stresses. Okay, practically not possible to have every material define the SN curve for different mean stresses. Okay, so what we do is we have the for example this case where mean stress is not equal to zero or greater than zero in this case. So you would actually plot this mean stress on the horizontal axis and your applied stress on the vertical axis, and you get the endurance limit of the material from here. Okay, so we actually know the endurance limit, and we have the ultimate stress of the material as well. So what we do is we actually join them. Okay, and this gives us the region that we are interested in, that will actually give you the infinite fatigue life. So if you notice here, for whenever you have a fully reversed cycle where mean stress is equal to zero, you will have whatever below the endurance whatever stress below the endurance limit is okay. You will have an infinite fatigue life. But when you have a mean stress not equal to zero, so even these stresses are below the endurance limit, still you will have a certain limit up to which you can have the mean stress. So if the mean stress is up to this point and you have endurance limit, this applied stress below the endurance limit, it is within the safe region. But the mean stress increases to this point, then you are going out of this curve and you are not in the safe region. And this curve that we actually drawn here, this is called the uh, okay, this is called the Goodman curve. Okay, so this Goodman curve states that if your mean stress and the applied stress are within this specific region, you are safe. It goes out of this region, you are not safe. You do not have the infinite fatigue life. Okay, so this is what the Goodman states, and actually we will solve a problem related to this in the next lecture. So I hope it is clear now, and if there is any question, please do ask. Thank you very much.